Hi everyone, welcome back to our machine learning series. You're here with us today on select and customize architectures and hyperparameters using random forest. That sounds like a lot of things to learn, but it's actually pretty good. We'll go through it nice and gently. Today I'm here with my good buddy Jason DeBoever. Hi Jason, how are you?
Hey Glenn, good to see you again.
Yeah, you too. You too. Now, for those of you who don't know your charms and wit and grace, would you like to introduce yourself to everyone?
Hi, I'm Jason DeBoever. I am Senior Product Manager on our content and learning material in Microsoft, and I focus on AI and ML content, much like the content you're going to be seeing here today.
Awesome stuff. And my name is Glenn Stevens. For those of you who've not met me, I'm a senior content developer working on the Learn Live team. Excellent. Shall we get into it?
Let's do. So, what have we been? Where have we been? Where are we going?
Well, we've been everywhere. We're actually covered 2/3 of the material. We had 9 sessions in the series on learning machine learning. And we're at that point, which is the middle one in the chart, where we're selecting and customizing architectures using random forest. And we'll talk about what architectures are in the concepts of machine learning, and also talk about random forests and decision trees in today's session and show how they're applied. Where we've been learning some of the fundamentals of machine learning, things like regression techniques, logistical regression, a simple regression, polynomial regression, and a range of other techniques for dealing with data, and so on. And we've still got a little bit more to go. We've got confusion matrices, which is actually not that confusing when you actually learn how it works. It's actually
What's
really
confusing? What's confusing is when we're going to be delivering that session.
Oh, that's very true, because you know what? Next week we have Ignite happening, which is a great conference that we hold every year. And this year we're holding 2. That's how awesome it is. And because of the Ignite conference, next week's session will actually be on I'm going to say the US Monday, because it's my Tuesday here in Australia.
That's right. So for those of us in the US, it'll be at the same time, but on Monday. And for those of you in Australia, it'll be at the same time, but on Tuesday.
Yeah, that's right. So that'll be the confusion matrix. That's the confusing part. Very well put, Jason. And then we'll finish off our series with optimizing model performance. So there's only 2 after this session to go. So if you've been following all the way through, thank you, and let us know if you've seen all of them as well. I think that's a special award there for something as well. But lots of fun to do.
We don't actually have awards for what it's worth, but boy, will we give you a hearty thumbs up.
And bragging rights. You get bragging rights.
Absolutely.
So if you want to follow along with today's session, you can. What we normally recommend is just watch the session, absorb it as you're watching it, and then you can go in and do the exercises after. You do that by visiting https://learnml-architectures. And if you remove the -architectures, you actually go directly to the learning path that has all the 9 episodes in there. We're option 2 in that learning path if you've not been there before.
Absolutely.
Cool. And what's our objectives for today, Jason?
You know what? When you were going over the whole list, you actually did a wonderful job of going over today's objectives too. We're going to talk about model architectures, including how we can tweak them with hyperparameters and what both of those words mean. And we're going to use a specific new type of model that we haven't looked at before, called a decision tree, and some of the other models that are part of that family. We're going to talk about today in order to frame our discussion around hyperparameters and model architecture.
Awesome. And we are very much live. And if you're following along, listening, let us know where you're calling in from. Obviously, I was mentioning before, I'm from Australia. Jason, you're from the wonderful Motor City, Detroit. And we're always curious to know where people are connecting in from.
Yeah, absolutely. And if you've been following along with us, you know it's live, because things don't always go incredibly smoothly, but
that's true.
They go all right.
and we know it's live because sometimes we get questions that are really, really tricky.
Exactly.
Which is good.
But speaking of those tricky questions, we have people helping out with those tricky questions on chat as well. So big thanks to our moderators who are hanging out on all the platforms that we're streaming live to right now, at least all the ones with chat boxes. So they're hanging out there. Of course, we like it when you're watching us directly from the Learn TV interface, which is one of the ones with chat box, and also the only ones where you can answer our trivia questions interactively.
Yeah, that's very true. So, but they will be moderating the other series as well, or the other places.
Yeah,
cool.
Absolutely.
All right, well, let's get into the core content for today. Jason, would you like to take it away?
Yes, I will. All right, so we've dealt so far with very particular types of models. Those particular types essentially are a variation on finding an intercept and a slope in a mathematical model, in a almost a geometric model, right? So finding that intercept and the slope there. But we're going to vary off of that now. And there are actually a lot of other ways we can look at our machine learning models. One of them today looks a little bit more like a flowchart. Actually, the one we're going to focus on all today can be thought of a lot more like a flowchart than that graph model that we've used for all the models we've learned so far. So we get to mix things up a little bit. It is going to be another classification type of model that we're looking at today. And Glenn, why don't you tell us about our scenario?
Right. So our scenario is based on some existing data we have on crimes that are committed in San Francisco. And what we're going to use the data for today is to actually predict whether or not a crime will be resolved. So whether they solve the crime or not, based on things like the location, the time of day, and the day of the year, et cetera, and all the data that we have. So we'll basically look at that data, we'll do some cleaning and organization on it, and then use decision trees and later other architectures to see how we can determine if it's solvable or not, or the likelihood of it being solved.
So a not good example of responsible AI would be, for instance, to use this data to decide where to commit my crimes.
Yeah, that would be bad. So yeah.
So I won't do that. Okay.
That's would you want to let do you want to let people know about responsible AI? Because I actually think it's a really important thing to learn as well.
Yeah, absolutely. We've definitely chatted a little bit about it in previous episodes, but it's always something that's worth coming back to. When we've got a lot of data, it's something we use to make predictions and make guesses. And there's a lot of different ways you can use that. We've seen that when our original data sources are biased. For instance, we see that if we're trying to train a machine learning model on who should be hired, but we use data historically on who has been hired, who has passed interviews. And that's clearly not something that's an unbiased historical data set. And therefore, training a machine learning model that way, and this is just one example, there are so many, it's well worth your time to look into. And maybe we'll do another set of Learn Live sessions someday on it. But when you're training your machine learning models on historical data like that, you're going to simply reflect the historic biases, because it's going to try to minimize the distance between the old biased data and the new model, which is not really what you want. You want to minimize the distance between a fair model and the model that we train, which of course is hard, because where are you going to find a legitimately fair model? So in cases where you actually can't, or where it's a seriously hard problem, it's best to just not deploy a machine learning solution. It's best to not lean on something that you know is going to be problematic and be unfair. And it's not just going to be kind of bad from a moral standpoint, but it can absolutely expose your business to risks and to obligations to make these things right.
Yeah, so we could talk about this for a long time. I know you and I personally have had long chats about this, but we've also provided a link to the responsible AI on this page as well. So for everyone listening, you may want to check that out after the recording, of course, or after the session today, which is totally live.
Totally live. All right, let's roll on our decision trees and model architecture discussion. So decision trees, this is our new model today. This is the new model type we're going to be discussing, decision trees and their variants. The way we can think about decision trees is as a flowchart, essentially. So it generates the flowchart dynamically based on the data. Now, for instance, let's think back to a previous module that we went through, a previous episode where we had our Titanic survivor data set. So with our Titanic survivor data set, we could train a decision tree. And what it would do is look at our data, and it would realize that the easiest way to segment the data in order to maximize one segment having, so obviously, I guess I should back up and say, what are we training for? We're training for learning who died and who survived on the Titanic. So in so doing, we're going to send that data into a decision tree trainer. And the decision tree trainer is going to see that, okay, the easiest split I can do is on the gender field. And if I split on the gender field, I'm going to have one bucket that has, I think, 73% survival, and another bucket that still needs to be further segmented in order to get to the ratio that we're looking for, the cleanliness, I guess, is a way to put it, that we're looking for. And by cleanliness, I mean we're trying to get buckets that are separate, where one bucket has survived and the other bucket has died, and then we can kind of trace the flow chart to see what decisions were made. So boom, we split it like that. And we see, okay, if female, we're going to be able to guess with our target accuracy. 73% isn't great accuracy, but it's apparently great enough for our simple model here. And now we have our bucket. However, when breaking that up and getting the male bucket, it was still too mixed up. So our trainer is going to find the next best thing to split on. And this is going to do this dynamically by looking at our data. And it finds that, okay, I think actually thinking back to that episode, it was something like age 10 made a huge difference. So if you were older than age 10, boom, you were strongly likely to die. And we see that was what our decision tree here predicts. If you're under age 10, then it goes to yet another split on whether or not you had siblings on board. And then finally, it was able to get to a prediction level that it's happy with. And that it's happy with is something that we can set. What does that mean, that it's happy with? Why did it stop there? Why, especially this one, why did it stop when we know there are other fields? We're going to talk about that as we get further into this module. Glenn, thoughts on our decision tree here?
No, I think it's interesting. It's certainly a lot less mathematical, I think, than our previous sessions. So where it's just got that generic split. You're making basically a lot of if-then conditions.
Yeah,
and they're just nested. Yeah.
Yeah, and there are things mathematical going on behind the hood, and some things that we'll definitely probably even hand wave over during this session in terms of magic. So under the hood, sure, but from a understandability standpoint, this is one of the great things about decision trees, not only from that standpoint of I have a decision tree model and I can understand it, but even just understanding what's going on. What is this machine learning model based on? It actually is a lot more understandable, I think, to software engineers, people with a developer software engineer background, which I think a lot of our viewers are in that camp, because of that kind of if-then statement sort of model.
Yeah, well, you see decision trees in business a lot as well, but normally the tree is going sideways and showing make this decision, then make this decision, then make this decision. So yeah, it's still quite a common scenario, I think, even outside of developer circles.
Yeah, absolutely.
Well, let's have a look at an example of one then.
So here's one where instead of seeing this tree first, we're going to look at that data side first. So we can see that this is some sort of athletic performance. You see there's a won a medal there on the right-hand column. And we've got two other features that we're using to try to predict whether a medal was won. And at a quick glance, it's not obvious what is the either right feature to split on or what the value would be that we would split on. However, if we pass this into a decision tree trainer, it's going to quickly find that the first node it should split on, the first branch of that tree, should be the age, and that the threshold should be around 24 years old. And we can see that when we did that, we split on 24. So now we have these two buckets that were split out by the decision tree. It actually did do a good job of finding that now in this bucket, we are 75% likely to not win a medal. And in this bucket, we have a 75% chance of yes, winning a medal. So that's a good predictor. That was a good thing to make our first split.
Awesome.
The great thing about decision trees is that they're really powerful. For a simple, easy to understand model, they're incredibly powerful. They can fit very complex functions because they are effectively doing a bit of logic and a bit of independent logic on every one of those decision points, on every one of those nodes. Now, that is incredibly powerful. That independent logic thing that I talk about is really powerful. If we think about our multi-input or our multi-feature regressions, even when of course we have the slope for each of those features. So each feature has its own slope, but they still have to be logical together. In other words, if we picture just that two-feature regression, remember there was a plane. So the answer had to resolve somewhere on the plane. So each slope had to go like this, but it's still a plane. To fit that complex function where we had waves and saddle shapes and things like that, we had to manually create additional features through either feature combinations or polynomial features where we squared or cubed a value. Or multiplied two features together, right? That's the only way we could create complex functions. Decision trees don't care about any of that. A decision tree says, okay, you have no function for sibling if you're in the female branch, and you have this function if you're in the male branch, and you could have some other function if you're in the male branch under 10 and versus over 10. And so those functions for each of those features are also mutually exclusive to all the features that came before, the rest of the tree above it. So it's fitting these incredibly complex functions right off the bat. Very powerful.
But I'd imagine that the way it maps out the data, like if it's got a training data set, it's going to be able to split exactly where it needs to, and it's going to have almost a perfect understanding of the entire training data set.
It certainly can.
well, that's really going to cause that overfitting, though, I think.
Yeah, exactly. Especially if we're not really careful, we're going to get exactly that. We're going to get overfitting very easily right off the bat, because the defaults are going to be to go fairly deep. And the other defaults, by fairly deep, I mean create a lot of nodes that really go down the tree and make a lot of decision points. And the other defaults, which may not be incredibly obvious yet until we discuss them later, are going to do the same thing. So we do need to make some intentional decisions in order to avoid this overfitting. Yeah, and before we jump into our demo, we do have a question. What do we mean by overfitting? And this is something that we've discussed in previous episodes, but and for a really thorough treatment of it, I would definitely advise going and checking out our previous episodes. But as a quick refresher, what we mean by overfitting is when the model, the prediction model that we're using, is too well engineered to the data set we used for training, but doesn't generalize and work very well with the real world. So of course, we have this training data, we have this historical data that we're using to try to build a model of the real world, but it's still only a subset. It's a very, very small subset of the real world, right? The real world has infinite data. Even if we have hundreds of thousands of records, that's still not enough to truly model the real world. So we need a model that doesn't lean in too hard to our training data. and can still generalize.
Yeah, right. And I think the example we had before, it's like playing golf, and you're playing golf on your local golf course, and you're really good at your local golf course because you know everything about that particular course, all the holes, all the hills, all the clubs you need to use. But when you go into other courses, you don't actually play particularly well because you're so localized to that particular golf course. And the data sets are like that as well. If you're so tuned to the data set that you trained on, you're going to be overfit for that data set, and you won't be able to apply yourself in the real world, really where it counts.
Right. Contrarily, if you were playing a lot of different golf courses, you'd learn to generalize instead of seeing that one hill that you recognize and know exactly which club to use. Instead, you will have learned to generalize. You'll see the flag and you'll be able to make a guess on how far away it is. And based on that, you will make your guess on the appropriate club that you use for those distances. So, I mean, I know it's maybe straining the metaphor a little bit, but it is a great metaphor for this.
Cool. All right. Well, let's jump into the exercise. We've got a few things to go through here. But we're going to look at decision trees. We'll build a decision tree. We'll visualize some of the data as well as we do, because that's always a good exercise. We'll do some data preparation to kind of change the shape. We'll go back and make some of the columns one-hot vectors. I'll describe what that is as we go through, and look at ways we can optimize the performance, and a little bit of pruning of the tree, which is a nice little gardening metaphor while we're at it. Let me go ahead and share my screen. Awesome. Hopefully everyone can see that. All right, so we're going to jump into this exercise. We're using Jupyter notebooks here, so I've activated the sandbox. If you're following along, you'll have a button here that says Activate Sandbox. You'll need to sign in order to do this. But we'll essentially be going through that data set we were talking about in our scenario, which is looking at the crime statistics. I think it's from like 2016 or 2017, and basically use that data to determine whether or not a crime can be resolved. So our first exercise is going to use the graphing library. We'll get this San Francisco crime CSV file. We'll read it into a pandas data set. So pandas is a panel data set library. And then we'll print out the first 5 rows and look at the shape, or how many rows and columns it has. I'll go ahead and run this cell, and we'll be able to step through it. It'll take a little bit of time, normally about 4 or 5 seconds. There we are. If I scroll down, then we can see the shape of the data and the structure, really. So here there's the category of crime, what day of the week, I think it goes 1 through 7, what district was it in, and whether or not it was resolved. Did they solve the crime or not? And the X and Y. But the X and Y is really latitude and longitude in this case.
Which is fantastic. When we have latitude and longitude, this is really a fun thing to do data visualization on, because first of all, if you just do a scatter plot and say, use that as your X and Y, which actually is why the features are called X and Y, it looks like a map with dots on it, although you can't actually see the underlying map, but the dots kind of show you the area that you're looking at. And then if you do overlay that scatter plot on a map, it like literally shows you, oh, it occurred in this neighborhood. You can see the neighborhood on your map. You can see the scatter plot dropping little dots or heat maps on top of it. It's really cool.
Cool. All right. So we've also got the day of the year and the time and hours from 0 through to 20, just before 24. And it's a nice shape, and we can see the size of the data set as well. So we've got essentially a little bit over 150,000 rows.
Finally, enough data.
We're always talking about using more data, don't we? All right, so it's a good mix of data. We've got some issues where we've got things like the category and the district are actually categorical. So we'll do some shifting with that. We'll change that to one-hot vectors in a second. We'll explain that in just a second. But before we do that, let's have a look at some of the visuals. Now, we always emphasize the fact that it's a good idea to have a look at how the data is portrayed, and that way we can kind of see any correlations that might be in place. And in this case, we'll look at things like the category versus resolved, like how many times a particular type of crime was resolved. Likewise, the same thing for the district. And then we'll look at, there's a scatter chart here of the GPS coordinates using that X and Y. And then also the day of the week, what days are more problematic than others, for example. And then I think that's our last chart. Oh, there's also one presenting the week of the year as well. So we'll go ahead and run this. It'll take a little bit of time, not too long.
Ready for it?
Yeah. Oh, there we go.
And there it is.
Cool. So our first one is the category. So what kind of crime was resolved? If you look at this one, so larceny or theft wasn't really resolved that much when we look at it. But if we look at what's this one here? Other offences.
Other offences.
That probably refers to things that were just caught at a particular time. But things like non-criminal or assaults a lot of assaults were resolved. Burglary, probably about a quarter, and you can see the trends based on the category. So,
and my favorite thing to do is look over like at the giant orange line right there, and this conversation that we had when we were looking at this data the first time. Look at the next one over, the one that relatively is a giant orange line, I guess I should say.
This one here.
I think we have like warrants, and I think some of these ones that are very clearly showing a high resolution. I think one of the interesting things about it is we notice that they're crime types that probably are instantly recognized. Say a police officer happens to witness it and just immediately makes the arrest, or there's they pull over someone on the highway, and that's where say you have banned substances, contraband that are found in the car, and so they make an immediate arrest there. Whereas something like larceny is more likely to be reported. It's not something that a cop is likely to find, a police officer is likely to find and make the immediate arrest and use that to create the file. So of course, the ones where the arrest and the creation of the report happen at the same moment are likely to be highly resolved. Whereas ones where somebody has to pick up the phone and say, I got robbed yesterday, please find out who did it, very unlikely to be resolved. So again, we have to think about our data in these ways to make sure we're not just putting blind faith in the fact that, oh, apparently if people are arrested for a drug offense, or if there's a drug offense report, it's very likely to be resolved. The reality is it was probably a report that was created at the same moment that the arrest took place. So
yeah. But that again goes back to some previous sessions where we've talked about the importance of having domain-specific knowledge for the data that you're working with. All right, well, let's keep moving. Our next chart is looking at things like the district that the crime took place in. You can see there's a lot of variation amongst the districts as well, whether or not it was resolved or not. It's interesting. I'd be curious to know the size of each district as well, and population and terms like that. Yeah. But here's the cool chart, the one with the map on it. It's kind of a little bit tricky to see, but the red dots in this case mean false, which is kind of the opposite of the previous chart. But the red is where there's the unresolved crimes, and the blue is where the resolved crimes are. So you can hopefully see some of the blue dots scattered throughout. There's a blue dot there, lots of red dots, but you can see a kind of a scan of the San Francisco area.
And again, driving home what you just said, the colors are reversed compared to the previous plots. So
yeah, exactly. So it's very interesting. And then if we look at the day of the week, we've got things like, it looks like Friday and Saturday tend to be our big problem days. And everything else is actually kind of consistent.
Yeah.
They're resolving the same amount of crimes roughly per day, but they're reporting more on Friday and Saturday. And
which surprises no one, right?
yeah, more people are out Friday and night, so things like assaults and things like that would likely climb. And then we've got the week of the year. So towards the latter part of the year, it tends to go up a little bit on average. But you can see there's various cycles, etc. But some interesting things to consider. So it's a good idea to look at it so we can see things like most crimes weren't resolved. You've got different levels of crime based on your district and based on the type of crime. Friday and Saturday had more crime, and larceny and theft were more problematic. So one of the things we want to do here is for the next step is to actually prepare our data for use. And at the moment, we've got that categorical data with things like the category of crime and also the district it was in. So for those that are presented as strings, we want to convert those into one-hot vectors. So for every value that we have in a particular column, we actually want to make a new column instead that's just a binary classifier like 0 or 1. So if we go ahead and change that and execute it, you can see we've got our category, which will change to category and then the type of category afterward, like arson, assault, bad checks, etc. And it will do the same thing for the district as well. And in fact, we end up with about, I think, 52 columns or 54 columns, pretty close. So we've just got to be mindful of that as well. But that's going to help in the classification as well, right?
Yeah, and just to repeat what you said, before we had this column called PD district, and it had a handful, 10, 20 unique values. So instead, what we've done is created a column for each of the potential unique values. Every unique value in the data set now gets a column, and now it's just each column is a binary yes or no. It belonged to Tenderloin, or yes or no, it belonged to. I don't know what any of the other districts are off the top of my head.
like the southern, but you would imagine that the binary classification now that we've got, is it the Tenderloin 0 or 1? That's going to be more useful in a decision tree rather than having to which value is it out of these 30 odd columns, 30 odd values, I guess.
Right.
So the next step we're going to do is we're actually going to split the data. We've got 150,000 roughly records that we can play with, and normally we go something like, we'll take 25% for the test data set or the validation set and 75%. But because we've got so much data here, we're actually going to just take 10% for the test size. So that's what this next block of code is doing. It's looking at data set, creating two data sets, train and test. Train is what we train the model on. Test is what we validate that the model's working well. And you can see that the size of the data, it's actually a pretty good split. I like having way more data than we've had in our previous samples for this one.
Makes everything feel nicer, doesn't it?
It does. You get a better sense of comfort. All right. So the next step is we actually want to make sure that we're executing it. So the next step is to actually fit and test the model. So we've got this method here that we're running through. We've got a few things that are happening. There's a features list here because we did that one hot vector swap, that we've got now 54 columns, and we want to make our features list, which is the inputs to our model, essentially all the columns except for resolution. Resolution is our label. So label means the output thing of what we're looking for. In our case, we want to know if a particular crime has been resolved or not. So we want to have all the columns in the data set except for resolution. That's what we're doing here.
So train using the 53 columns, all of them except resolution, yeah, and then compare it and measure against that resolution column.
Right.
Yeah.
So, and that's what this code block does here. It'll essentially call fit, which is the training method, against these particular columns with an outcome of getting this particular resolution. And then we actually just measure at that point, and then we return the training accuracy and the test accuracy. That's our fundamental that we'll use, not only in this exercise, but also in the next one as well. So then we go ahead and fit the decision tree. So in this case here, we're essentially using, so unhover over that, the decision tree classifier. So that's going to create a decision tree for us. It's going to pass the random state of 2. So we'll talk about seeding a little bit later, but it's basically an initial random number value and then maximum depth. So how many tree levels do we go down?
How many splits does it do on as it's going?
Oh yeah. So you normally get essentially a tree with, I think it's max depth plus 1 in the output. So if we do that, then we can look at the training accuracy as well after we've fit and tested the model. So our training accuracy is roughly 68%, and our test accuracy is about 67%. It's not awful. It's actually pretty good. It's better than
it's consistent.
Yeah. We get a sense of how it works. We get a sense that it does work. We actually don't get a sense of how it splits at the moment. And the next mechanism here is we're actually going to visualize what that split looks like. So we'll get the tree and we'll actually display it. Some of these great. Python libraries.
That's one of the great things about keeping our trees shallow as well, is we can rationally do this and actually get a look and see what it's splitting on. And so we can see exactly what's going on. This is very cool.
So we've got thefts. If it's theft is less than 5, then we'll split it, and we'll go to the left, and we'll have the warrants will be the next decision. And on this side, we've got the district is being detected. So even at the same level, they're not basing the decision on the same feature. They're actually looking at different features because they're more related to the context of where they are in that decision tree path.
Yeah, exactly.
That's quite nice. And you can see the split here. It's splitting again. This one's based on the location. And this one here, strangely, if the day of the year is less than 209, then it's likely to be resolved.
And that's what the color coding is too, by the way, folks. That's the you'll notice that's that orange versus blue correlates with whether that bucket is a largely resolved bucket or a largely unresolved bucket.
Exactly. And that just drills down. The way I've been looking at this is that if the number on the left is bigger, it tends to go on the left. If the number on the right is bigger, it goes to the right. And that's how I've been following it as well. But yeah, there's just different ways of splitting, but it looks at that data to define what the splits are. And we've got a hard stop here at the maximum number of splits here. Okay, so we've actually got a question here too, which I think is kind of interesting. You're showing us how to use decision trees to build classification models. Is it possible to use this for regression tasks as well?
It is possible to use decision trees for regression tasks. Let's actually talk a little bit more about that. We're not going to drill into it, but we can talk a little bit more about it when we get to random forests. It actually becomes a bit more of an interesting discussion with the random forests variation of decision trees.
Cool. Yeah, I agree with that there too. Awesome. So let's have a look at the decision tree classifier again, because if we looked at the last code block, I think we only went to 3 depth levels. But what if we trained it on 100 depth levels? I think that would be a tricky thing to visualize, but we can certainly go ahead and run that and then see what the model's like. And if we look at the data here, we've actually had a jump. Well, the training accuracy looks very, very fit. Like it's almost classic overfit, like it's a perfect score nearly. And then we've got a test accuracy, which is 0.77. And I think that's a slight improvement of what we had. I think it was 0.6 something from memory.
Sure. Yep. I think you're right.
Yeah.
So it is better, but we also know that we're overfitting.
Yeah, for sure.
So a little aside on the overfitting thing too, what that means is, even though we did get better in the test accuracy as well, you might think, well, of course it's overfit, but we're better in the test accuracy, so it's still better. And while that is true, anytime we're overfitting, it's a virtual guarantee that it means we have too much complexity. Too much complexity also maps to a more resource use. In other words, it's a more expensive thing to both train and execute because it's a more complex model. So you may simply want to be optimizing and reducing complexity for resource purposes as well. Now, a lot of times these things are very inexpensive to actually do inference on. In other words, the production time predictions. So maybe you don't care so much about that part, but it's yet another consideration.
Okay. Cool. And to show some of the overfitting or continue on with the sample, the next code block, what we're doing is we're actually just shrinking the training set to 100 records. And by doing that, then we'll actually probably see an even more exaggerated version of overfitting. So in fact, we've got our training accuracy at 1. You can't get any fitter than that. But our test accuracy is actually decreased as a result. So
we know we have too complex a function, just literally just memorizing our training set. And we that smaller training set, of course, is easier to memorize, but also we're now not doing a very good job on our test set at all.
Yeah, exactly. Cool. But then we get into the process of pruning, which we hadn't really introduced as a concept before, but pruning is basically like you trim a tree. So there's a couple of different types. There's pre-pruning and post-pruning. Jason, do you want to explain those concepts?
Well, I mean, one is an analytical approach, which is not what we're going to do here right now. But what we are going to do with post pruning is literally just train models and see at what point they start. It's kind of a variation on something we use in other types of models, other types of training of early stopping. And it basically means we're going to look at various increasingly complex trees and see when they start to diverge. And when they start to diverge, and by diverge, I mean the train set and the test set are starting to get different performance characteristics. That's where we'll realize this tree is too big, hence the name pruning. This tree is now getting too big, i.e. too complex. And therefore, we're going to use a smaller version of it. And we'll just go back to one of the previous three trained ones often enough.
Yeah. So if we look at this code block, what we're essentially doing is executing the same model as before, but we've got an array where we're defining a number of values for the maximum depth range, and we'll graph it. So when we can see the range of data, we can actually see where we need to prune as well. So we'll run this data set. It'll execute all of it. We'll end up with a graph at the end. And you can see that here. So here's the max levels of depth. So roughly around 9 or 10. I think 9 is the better value, just by a little bit. So that particular value here is really where we should be using the value for the maximum depth to get the best outcome against the test data set.
Yeah, any more, basically when we get into these much deeper, more complex trees, all the way up to 90 and 100 levels of depth, we're not getting ourselves anything in terms of generalizability or in terms of our test set or presumably our real world predictive value.
Right. Cool. So we'll shrink. In this case here, we'll do some shrinking on the data set as well. We'll look at the not pruned version, and then we'll look at our final version as well, which is pruned, and then see the differences within the results. So in the unpruned trained accuracy, we get a lot of overfitting, really close to 1, and the test accuracy is 0.72. But where we're not doing the training, it's 0.8 for the train accuracy, or not doing the pruning, it's 0.8 for the training accuracy, but 0.74. So it's actually better in the real world.
Yeah.
And to be honest, the maximum depth that I saw that was the highest was 9. So I feel like running that again.
You feel like seeing what we can do.
Yeah, like I want to be a stickler for the best value here.
Right on.
But we can see the test accuracy is increased a little bit as well. So it pays to look at the data and just work through it and get the right result. Yeah.
Good sticklering.
Cool. That's our look at decision trees. Well, at least for this exercise, we'll be using decision trees in the next couple of exercises as well, because random forest is based on the knowledge that we've learned here as well. But back to the slides.
All right, so decision trees are basically our flowcharts. So our random forest is a variation on that. And beyond even just talking about varying to going to random forests, because they're more complex and therefore they must be more cool, which we already saw that that's not true, because we made our trees more complex and they got less cool. But random forests certainly are interesting. So what we do with a random forest is create multiple trees. So instead of having just that one tree and splitting on the data and kind of letting each example flow through it, kind of drop through it, what we're going to do instead is create many trees. Each tree is going to have only a subset of the data, and that subset can vary drastically. But because each tree only has a subset, it's going to end up finding different split points, different breakpoints. We are essentially going to end up creating a lot of different flowcharts, each based on a subtly different subset of the data. Now, it's not like if we had 5 trees, we were going to have 20%, 20%, 20%. Instead, there'll be heavy overlap. We may have hundreds of trees, and each one has 80% of our data. We also may use subsets of the features instead. So in that case, we're going to, actually in all these cases, because we have less data, whether it's less rows or less features, we're going to, by definition, be creating less complex functions. And so we're less likely to overfit. And because we don't have all the data, we can't overfit all the data on each one of those trees. So each one of those trees will be not accurate. They may even be overfit. But what we can then do after finding all of our subsets of data, we can then combine those trees, combine what their guesses are, and essentially vote. Each of those trees will essentially vote for every example. So now we're going to want something to be predicted. We're going to drop it down through the flow charts, and each flow chart is going to come up with an answer for that one based on the splits that flow chart did. It's going to come up with an answer, and then each tree is basically going to vote. Majority wins. If it says it belongs in this category or that category or that category, we're going to make that be the essentially the correct one, the correct answer.
Yeah, I always find this interesting. I think I was mentioning this to you the other day that it for me, when I heard about random forest, it actually sounds like the same technique as crowdsourcing, where you get lots of independent choices coming together, and the smoothness of those choices is more likely the accurate one.
Yeah, and it's actually it's insanely common and powerful technique in machine learning is the concept of ensembles. And an ensemble, the random forest is the simplest and usually taught first ensemble method. And that basically, an ensemble is basically having a lot of different models and letting them vote or letting them combine to decide what the optimal answer is. And it helps whether it's just all trees, all slightly different trees, whether they're trained in parallel or whether one tree helps to inform what happens to the next tree, which is we have different decision tree ensemble methods that can be done that way, where you train one tree and then a next based on what happened here. And we're not going to get into that today, but that's something known as boosted trees. Regardless, that, like you said, that smoothing, that averaging of having a lot of different opinions, for lack of a better term, helps smooth the individual biases.
Awesome.
That's exactly what we're talking about here. And the reality is random forests are extremely powerful because individual decision trees are extremely powerful. And then the that smoothing function helps to alleviate the downside of the power, that is the overfitting. So random forests are very popular and fantastic. They're relatively inexpensive as well. Now, of course, you create more trees, that's more flowcharts. So you can start to make the cost matter. But compared to other powerful things like deep learning, or even some of the boosted tree techniques that I talked about, where those boosted ones, you have to go in series, and so they can't parallelize as well. Random forests can parallelize very well. So they're fantastic. Their biggest downside is that once you have a lot of trees, it can be hard to make good intuitive sense of the combination of decision points, even though it's fairly obvious what each tree is doing because it's a flow chart. The combination starts to become a little bit hard to reason about.
Okay.
And finally, we're going to be able to do things with these, like decide how many trees we want. What is the depth of each tree? In other words, each tree, how many nodes? How many features do we pass in? How do we split the data? In other words, does each tree get 80%, 90%, 50%? We have a lot of these different decision points we can make. We'll look at a few of these, but then when we come back, we're going to talk a lot more about those decision points in general.
Awesome.
First, let's do the looking.
Yeah, all right. Let's have a look. All right, so we'll jump over to the demo again. So this is exercise 2. So we're going to look at random forests, but because they're based on decision trees, we'll actually run some of the code that ran the decision trees before, because we want to use that data for comparison. Remember, we've got our method for analyzing how well it's running on the training data set and the test data set. We want to use that consistently to see if we can improve the numbers that we're getting and improving the result, especially on the test data set.
By the way, back to that question that was asked at one point about using decision trees for continuous values. And I said, we'll come back to it when we talk about random forests. So the reason it's more interesting to talk about continuous values like regression style predictions with random forests is because you can get closer to a truly continuous value with a forest. With a decision tree, you still end up ultimately with a bucket. It still has to make a decision and create a bucket, which is roughly a range. But with a forest, it's able to make those decisions a lot. And then you can take a mean, you can take an average. And because you have a lot of those buckets, the average actually ends up getting a lot closer to what you're interested in, or to the correct and accurate target value.
Cool. Now, actually, before we get to the demo, there has been a question that's been there for a little bit of time. I want to make sure we get a chance to answer it. Someone asked, can decision trees handle categorical features without the need to encode as one-hot encoders?
So it's my gut instinct is to say no. I will. So what I can tell you is that there are plenty of libraries that will do the one-hot encoding for you, but to my knowledge, everyone is going to do the one-hot encoding. I mean, I could sort of imagine a scenario where it actually did hard split on the string exactly equals this, and if it doesn't, then go this way, which is largely what's happening when it splits on one of the one-hot encoded features. But to my knowledge, every library that doesn't require you to do the one-hot encoding yourself is actually just doing it behind the scenes. So I can't guarantee that's the case, because like I see it set, I could sort of envision it being possible to do it without, but I wouldn't advise it.
Yeah.
And I don't think there's any that do it that way.
Cool. Thanks. Now, the next thing I wanted to mention is we're going to go through the samples. So I'm just going to run this one here directly.
Another point about what I just said too, splitting on a string, is even though we're thinking about these all as flow charts and if-then statements, there's a lot of optimizations that happen under the hood that much like a compiler. So if we're doing things like that, it's probably a lot harder for it to optimize compiler style. So I highly doubt that any are doing it without doing the one-hot encoding under the hood.
Yeah. Awesome. All right, so looking at this data set, again, we're opening up the San Francisco crime level. We're doing the one-hot encoding on the category and district. Then we're splitting our data set and then printing out the details of that. So if I scroll down a little bit further, we can see our data set. Should be 54 columns and then 5 rows, because it's just printing the head of the data set. And we can see that this number of rows here, and for the training data set, and also for the validation data set too. Now we've also got our other code that is used to measure the model. In this particular case, we've got our features that we're looking at, everything except resolution, and then we've got our fit and test model. I could just go ahead and execute this.
All like before.
Yeah. And then we get to our decision tree. So we're going to run the same decision tree that we did over the other data set. It's running at the max depth of 10. I'm just going to leave it there for now. A
little bit of a baseline.
Yeah. So we've got our test accuracy at 0.759. So that's not too bad. So roughly 76% on the test data set. And this is where we get into the next section, which is on random forests. So remember, the random forest is a collection of trees that are stuck together, and they're smoothed out, the ensemble technique that Jason was talking about before. So here we're using the random forest classifier, We've got that number of estimators as true. That's really saying the number of trees, decision trees that we're creating in this case. So there's only 2 trees in our forest. You can probably see the forest from the trees here. And we go ahead.
It's a random copse of trees.
Yeah. So our trees are created here, and we've got our test accuracy, which is 0.73. And look, we've only got 2 trees here at the moment, but our training accuracy is 88. We're more interested in the test accuracy, though. So 73% at this stage.
So the story we're getting is that 2 trees isn't enough to create that kind of blurring and smoothing function.
Yeah, like if you saw 2 trees, would you call that a forest?
I would not. I already called it a copse. And even that's a stretch.
Right. So we're going to apply the same technique that we did before, where we'll actually run through a range of values, 2, 5, 10, 20, and 50, and actually see the number of trees and how that's going to reflect in the test scores. So we'll essentially go through that process again, creating the random forest classifier with the number of estimators, which is in that array, and we'll go ahead and fit and train the model, and then we'll output that to some arrays and then graph the results of those arrays. And we should get an idea of how many trees are really going to create a better result. So it's taking a little bit longer to create these trees, though.
It is.
Yeah.
We've got a lot of them.
Yeah.
Not too terribly surprising that it has to do some heavy lifting. Is this one actually the one that's going to try to take a couple minutes on us, or this isn't that one?
No, this isn't that one. There's one that'll be a little bit longer. I think that might be in the next exercise. But you can see here as the number of trees go up, like 5 is a much better number than 2 in accuracy. It's like nearly at 0.8. As we go along the tree, 0.81, I think 50 was the next entry, 0.815. So probably 50 based on the values that we have here. But we can see a steady incline, but it also might be that the more we go up, it's going to be a negligible value as well.
We're certainly hitting diminishing returns, but we're also still getting better. So yeah, I guess we're going to have to make some judgment calls, right?
Yeah, but considering we don't have half an hour to run a model, well, let's just set it at 50 based on this one for the day. Yeah. And it's showing up twice in here as well. But that's because the show equals false. One of the things about Jupyter notebooks, it'll output the last object that's created there as well. So in this case, that shows the chart twice. I normally execute that, but that'll take about a minute and a half to execute again.
Yeah, no need to do that now.
Right. So the next thing we want to do for our architectural decisions with the random forest is to actually specify the minimum number of samples for split. So if you've only got, say, for example, 5 samples, you might go, well, that's not enough to actually split at that point. Like you only want to split if you've got more than 5, for example. I think the default is set to 2, so you can just split on either of them. So if we look at that, we're going to do the same thing again. We'll set the minimum sample split to a range of values, 2 through to 500. And then we'll go ahead and create the models again, just with our minimum samples that are being passed in. We'll chart it. And then I'll actually go ahead and run that because it'll take a little bit of time.
Excellent.
And then we'll be able to see the data set. It's a little bit quicker than the other one. But again, you can see the diminishing returns here as well. So the minimum sample split, if I go further along, you can see the accuracy 6.8, 6.9, 6.99. So about there. So looks like 20 is the better value here for the minimum. Yeah. Otherwise, we're getting our values are decreasing.
Yeah. Right. What we would expect is that, and in fact, it's kind of interesting that it is flat even at the beginning, because often if we have too small of a split, like you said, if you have one or two things in each bucket, you can be overly complex. On the other hand, if each bucket has to have 500, you're not going to make very many decisions. It's going to be underfit drastically. You're not going to make enough decision points to really fit any meaningful function at all.
Right. Cool. But at least looking at the data as well, we can come to a reasonable approximation of what a good value for our model would be. And then lastly, I think we're looking at the model depth. So how many decision splits are we going to make within this? And likewise, we're going to do the same thing again, 2, 4, 6, 8 to 100. I think this is the one that's going to take about 1 to 2 minutes, Jason.
All right, well, you better hit it.
Yeah, I'm going to hit run.
And
it's there.
And we'll recall that we did do something similar in our first exercise. We did exactly this. We looked at different depths, but when we looked at different depths there, we were doing it for a single tree. Now we're doing all of those depths, all for 20 different trees. It looks like I'm looking at the number of estimators there. And so each tree will have a maximum of two nodes, a maximum of 4, a maximum of 6 as we do that loop. It doesn't look like it's the one that took forever because it looks like it's done running. Am I wrong? Yeah, there it is.
Yeah, it's actually pretty good.
Wonderful.
And then we can see the performance there again. Our test data set is shown in red, and it's not performing too well until we get to about here, which is our depth level of 15. Yeah, it looks like the maximum depths of 15 is the good value here today. So we can look at that chart and keep that value.
So that would be kind of that would be that pruning really that we talked about in the first exercise. We'd be limiting ourselves to 15 in that same way that we talked about in the first exercise. Yeah, and exactly. You'll notice too, in the first exercise we stopped at 9. Here we kept going to 15, and that's because the forest is allowing us to fit a more complex function while still being generalizable.
Yeah. Cool. All right, now let's move on to our I think our last step here, which is looking at the optimized model. So we've got the right values for the random forest, the maximum depth, the maximum features. So these are the ones that have all been pre-chosen and analyzed. And go ahead and run this. We actually should be able to see the values of it as well, and also look at the training and test or validation numbers as well.
Oh, this may take 1 to 2 minutes. There we go. We found it.
Yeah.
You know, it may actually even be worth it. We can go to the slide deck and come back to this. Take a quick peek at this as we also go to our next exercise if we want to do it that way.
Sure, we're probably only 30 seconds away from it though. It'll be flip-flopping
very
back.
Well.
Yeah.
I talked about it long enough that we're only
but it's kind of interesting to look at the improvements of the model over time as well. It's that basically whittling away the edges and finding the right values, doing that repeated step of visualizing what are the range of values, what value is going to give me the most benefit, and then constantly using those values to get to the optimal model. And I think that's a really important process just in general to be aware of.
Yeah, and you can see that we're using a lot of the different values that we looked at here. So we got max depth, we have max features now. We really didn't talk about, which we should have. Max features again is using a subset of the features, a random subset of the features in each one, just like we're using a random subset of the rows. And so we've got the min split as we discussed before. So a lot of those things going into what hopefully is a optimally smooth model at this point. We're getting real close to 2 minutes. Let's go.
We are. It's I almost can't wait. It's so exciting. There you go. 1 minute 40 seconds. But then we can see our
such a subtle output.
But our final random forest, we get 0.81, which is much better than the decision tree that we had at the start, and then an improvement over the previous sessions as well. So
that's very solid improvement.
Awesome. So that's our look at random forest. We'll jump back to the slides now. We'll still be looking at random forest for the rest of the section.
Yeah, but we're going to talk now about hyperparameters.
Cool.
And even as we went to this last exercise, I mentioned that we would be discussing hyperparameter, or well, I mentioned that we were going to be discussing settings for optimizing our training and optimizing our models, and the tweaks we could make in addition to selecting a model architecture. Like in addition to, hey, we've decided that we're going to try a random forest, but what then can we do to start modifying those things? Those decision points, those things that we can tweak, are known as hyperparameters. And there's a reason for that. You may think, hey, the things I can tweak when calling code, those are just called parameters. So are hyperparameters somehow more parametery than regular parameters? And perhaps, maybe the answer is yes. So in machine learning, the term parameters is already taken. In machine learning, a parameter is those things that we train. So when we talked about our regression models, our intercepts and our individual slopes or our individual coefficients for each feature, those were trained and those were the parameters. So the things that we can train are the parameters of our model. And in our decision trees, random forests, the parameters are the split points. They get trained. The training process finds the optimal split points. Those are parameters. And so the things that we tweak to help it make decisions about training parameters are the parameters for training the parameters. Hence, they are maybe more parametery. But anyway, regardless of whether it really makes sense, it's the term that the industry has settled on.
Yeah. I personally, I think of the hyperparameters as really, they're just configuration settings for your model.
Yeah, exactly. That's it. That's much more succinct than the way I said it.
Well, you had to explain why parameters couldn't be used as well to define it.
Yeah, we've already talked about this a good bit in terms of what we can do with it on random forests. We talked about the depth of the individuals, trees, the criteria that we might use to split on. Now, the split criteria, it turns out, is maybe a little bit more complicated because we do try to optimize the performance. And so we don't literally kind of go through every single possible combination of splits. Instead, there are heuristics that are used or guesstimates that are used, and this is some of that magic compiler math under the hood stuff. We can affect what guesstimate algorithms they use. That's not the technical term in this case. Hyperparameter is the technical term. The guesstimate here is not, but we can affect how it splits those, what heuristics it uses to predict what's optimal split. We can affect how much it's willing to improve. So minimum impurity decrease is, if you think about it, a really fancy way to say a way to get less wrong, which is exactly what we said way back in episode 1 that machine learning is entirely for. So what's the minimum amount we should be willing to get less wrong in order to do a split? In other words, if you can't improve it by more than this, don't bother splitting. We can change the number of individual features. We talked about that. We actually did do that in our previous exercise. How many features are we going to include in each tree? And, the seeding thing, this is an interesting one because while in practice, we do see that when using randoms, which we do all over the place in machine learning code, when using randoms, we see in practice that we do set the seed to some value so that it's reproducible, because we're going to keep running that code over and over again, and slight variances are annoying when trying to look for patterns. That said, you should only see slight variances. If you're setting your random seed, so if you're setting your random seed to something different and it appreciably changes the results, you've got a problem. So this, whether or not you really want to call this a meaningful hyperparameter, I'm a little on the fence for, but we have it here.
Yeah.
Random seed.
Yeah, I'm not a fan of having something as a parameter that is kind of down to luck.
Yeah, exactly. All right, we've got our demo coming up again.
Right. Cool. It's demo day today. Nice. All right, let's jump over. So we'll look at essentially looking at tuning with the hyperparameters in this example and going through a lot of those hyperparameters that Jason was talking about before. So our first step is essentially going to combine all those mechanisms where we have bring in the data set, doing the one-hot vectors, making sure that we've got our method to test how well our model is doing, essentially, and then printing the shape. So this should be actually a fairly sizable portion of code. Here's our shape, 54 columns. You can see all the categories and districts in our data set, and we also want to split our data as well to get the appropriate data set.
We did get a request to do a quick explanation of random state, and yeah, absolutely. So when we use our deterministic hardware, when we use our CPUs, our GPUs, and all that to try to get a random number, there's not really a way to get a truly random number. So instead, it's deterministic based on some seed. It runs an algorithm and pulls out a number that's hopefully at least properly distributed in order to be what we call pseudo-random. That said, the seed usually is going to be something like an internal machine clock or something like that, but we can tell it to instead use a number that we hard code. When we hard code the seed, then the deterministic code will run to grab a number out of the distribution, and it's going to be the same one every time because it's based on the same seed. So while it's seemingly random in the sense that it's not something I could consistently predict what I'm going to get, I will get the same one when I run the same code with the same seed every time. So hopefully that makes sense. It's a way to get a random-ish number, but have a whole set of code run the same way over and over again.
Yeah, I personally find it's better for us demonstrating this concept to everyone so we can have consistent results, consistent charts when we train. But in reality, I prefer not to use the random seed. Do you prefer that level of randomness in your stuff, Jason?
Realistically, again, it could be the data analysis can be much easier if everything is actually showing is exactly the same. So that even if you have some slight variance, you know that it was something you did. That's true during the data analysis phase, but at the end of the day, and because it's true during the data analysis phase, you'll often tend to just kind of ship that way, to be honest. But realistically, once you're happy with the process, how the training is running, what other hyperparameters you have, and all that, theoretically, you should be able to not have to rely on that random state being set to a specific seed. Practically speaking, I don't think it matters too much either way.
Okay, cool. Well, let's move on. I know we've got a limited amount of time left. We're going to look at our first criteria to split on, which is called a criterion. And the criterion is actually determining like a method of splitting. And there's two here, one called Gini and one called entropy. I'm not sure if we've explained those before, but there's subtle differences.
Yeah, so this goes back to that hand wavy magic math that we use to do the split. So when we're deciding what buckets go or what data goes in which buckets, and it's based on finding the optimal split, it doesn't really do an exhaustive NP-hard search of every possible path for splitting. It uses some sampling and some algorithms to make a good guess. These are just different techniques for sampling that are mathematically rigorous, but beyond the scope of this discussion.
Right. But looking at our model, we can go, okay, it looks like entropy is performing better than Gini.
Right. Right. In other words, it's a thing to play with.
Yeah.
The setting to play with.
It's a configuration setting. If it works better, use that. Right. Nice. And then we've got our minimum impurity decrease, which is how much do we increase by to when we get to the point where it's not improving, where do we stop? That's what you were saying before, right?
Yes.
Yeah.
Yeah, when it's
Cool.
not improving by enough anymore, right? And this is the definition of enough. So when it's not improving by enough, don't keep splitting.
So in this example, we're going to do a similar, I think, visual again. So we'll use this with essentially the minimum impurity decreases basically between 0 to 0.0005 and 100 splits across that space. And then we'll chart that decrease and get a sense of where it would work. Waiting for the chart to display.
I didn't recall this one being one that took us a while.
No.
It is. Well, there we go. It's cranking along.
There we go.
Hey, we got it.
And we can see the chart is there. You can also see there's just variation between it. So it actually may not be that this is really a factor that's going to influence it at all.
Yeah, well, we can see it. There does seem to be a bit of
a
drop, but there's also an awful lot of noise. So
yeah. So I think that's probably about the value there.
Yeah.
That would be optimal based on the data set. Okay, and the other aspect is the maximum number of features. We kind of lightly touched on that in the previous example, but we've got 53 features that are going into our data set, and we could essentially limit the number. So in this case here, we've got a max features, which is a range between 10 and the length of the features plus 1. So I think this is kind of probably not written the best, but it's essentially a range of features that we want to use whenever we test, and what would be the optimal number. Again, it's doing that same visualization process.
So it's going to try, it's going to try doing 50 trees with 10 features each. Then it's going to try doing 50 trees with 11 features each, etc., all the way until it gets to all of the features, essentially. So it's creating 50 trees times all of the features minus 10. A lot of trees.
So then we can see the values here again, and they're all hovering roughly around the same area.
Yeah, it's super interesting to see that, with this data, once we've found our way to smooth the complexity, the further features or the further hyperparameter changes are not really affecting things tremendously much.
Yeah, it looks like
it's good.
It does reasonably okay between 20 and 27 or so. And then after that, it slightly drops down. So it's one of the nice things about the random forest, where it smooths out the biases. So maybe if we have too many features, it's not actually smoothing out as well as we'd like. All right, and here's where we get to seeding, which is the random number generator again. Again, it's probably not really that much of a hyperparameter, but it can be used. And we'll go ahead and do the same thing again. We've got a range of seeds between 0 and 101 in this particular case. And all I'm seeing is noise again. So it doesn't look like it's really helping us that much. Maybe we pick a particular value that's high here. So for example, what's this value here? 42. It's the answer to the life, the universe, and everything, apparently. But it looks like that's probably the optimal value for that if we had to choose one. But it's certainly, it's a little bit white noise.
I mean, to some extent, we do have to choose one. There'll either be the one we choose or defaults, but yes, I mean, it doesn't seem to be something that's going to be super impactful, right?
Yeah, exactly. So I think that's a look at the hyperparameters we're configuring for the random forest model. Anything else to add, Jason?
No, I think we have just enough time to maybe get a couple knowledge check questions in. Shall we rush back to the slides?
Let's do it.
All right, working on it here. Well, if I can't get PowerPoint to play nice, maybe we don't have time. Oh, here it goes. All right, we are Operational, and now I need to share my screen. Bammo. All right, so everyone head on over to that URL, aka.ms/learnlivetv. And Glenn, can you ask me a question?
Well, I quitted it. Yeah, I was just waiting to actually see your screen. It wasn't popping up there before. All right, question 1. Decision trees are classification models that A, typically have excellent generalizability to test sets, B, can only make binary true or false predictions, or C, at higher risk of overfitting their training data.
All right, so everybody give us some answers too. And I will also give an answer. All right, does it typically have excellent generalizability to test sets? No, not automatically, not off the bat. How about can only make binary true-false predictions? Nope, we've seen it work with multiple categories, so that's not right. So at high risk of overfitting their training data, which is essentially the opposite of A, and this one actually is correct. Yes, they are at high risk of overfitting their training data, but we, of course, have our techniques to mitigate that.
Cool. Yeah, which we applied with the random forest as well. Nice. All right, question 2. Actually, just looking at the chart here, we've still got some votes coming in, but it looks like we've got a split of votes.
We do.
I feel like there's a little bit more, but essentially most people have answered that correctly at a high risk of overfitting their data. Cool. Let's move on to question 2. Question 2.
I think we only have 2 questions here, so this will be our final question.
All right. What does selecting model architectures mean? Does it mean A, picking a model's parameter value before training, B, deciding how a model will be structured, or C, selecting a 32-bit or 64-bit compilation option?
Yeah, so it's probably 32-bit versus 64. No, I'm kidding. It's not. That's a very different meaning of architecture. Maybe it's about asking how many bedrooms you're going to get. Then, if that's also a different meaning of architecture, not those. Let's jump up to A. Is it picking a model's parameter values before training? That's wrong for a couple of reasons. For one thing, it's just not what architecture is. But also, of course, we might pick hyperparameters, but parameters are things that are trained. So it's definitely not A. How about deciding how a model will be structured? That is true. I actually like to think of it more as the template of a model, because you start by selecting, say, that you're going to have a binary tree, a decision tree, or a random forest. So you make that template decision, and then between your data and the training, you end up getting to that fully formed model. So it's like, I like to think of them as templates for a final model, but model architecture is the proper terminology. Cool.
And that takes us to our summary, or our end slide for today. We've actually covered a fair bit, and it's been fun. It's been a step away from the kind of the mathematical constructs that we've had in previous sessions. But yeah, certainly looking at decision trees and random forests. Anything to add there?
Yeah, so like you said, we looked at this new model type, decision trees, and its most common variant, or one of its most common variants at least, which is to ensemble those trees into a forest, a random forest. And then we use that as kind of the anchor point to talk about hyperparameters and what those are and why they have such a cool, fun name instead of just being called regular old parameters. All right, let's remind people about what we've got going on in this series, in particular next week.
Yeah, so next week is the penultimate in our Learn Machine Learning series, where we're looking at confusion matrices and data imbalances. So it's actually a fun little module to go through. And while it's got the name confusion in it, it's actually not that confusing. It's actually very visually
confusing. You said penultimate. What's that mean?
Penultimate means the second last. So,
second from last. All right, got
it. Yeah.
And don't forget, that one is happening a day early. So 24 hours earlier than we usually do our sessions next week, because on our US Tuesday / our Australian Wednesday, we'll be having Ignite.
Yeah,
Of course, that actually goes for multiple days, but we will be broadcasting on Monday in the U.S., Tuesday in Australia, and other points over there.
a day earlier than what you're used to, essentially.
Yes.
From the series. But yeah, certainly sign up for Ignite as well. There's lots of great content that's going to be demonstrated there. Lots of good things for developers and admins and all sorts of people.
If you want to get more of
chat.
me,
Oh,
if you
yeah.
want to get more of me, you can watch our well-architected Learn Live session. That's going to be November 3rd at 10:30 Pacific Daylight Time. So adjust as appropriate. But if you just can't get enough, Jason, then you can check that out on November 3rd Pacific Daylight Time at 10:30 a.m.
Awesome. Cool. Let's see if we've got any questions in the chat.
I do not see any yet.
Might have time for one or two.
Yeah.
We did have some good questions coming through for today's session already.
Which was nice. We did. Yeah. Give them a couple minutes just to see if any new ones pop through, since we do have a couple minutes to spare on it. Once again, don't forget, folks, next week, tune in 24 hours early for this series. And you can also find me on Wednesday talking about our well-architected framework. I like to get all over the place. A little bit of well-architected, a little bit of machine learning over here. Now, machine learning is definitely my focus, but the well-architected stuff is just super important for anyone who's using Azure at all. So, so that, of course, is a lot of machine learning folks too.
Excellent. Now, just a reminder that if you want to essentially go through the exercises that we've done today, head over to https://learnml-architectures, and you'll be able to go through and enjoy the same process. Spend some time in those Jupyter notebooks, changing the values, experimenting. It's lots of fun, really convenient to do. You don't have to set up any infrastructure. It's all built in to the web page, which is really kind of delightful.
It absolutely is. All right, we have one question. All right, we do have time for. We have one question. We have time for it. So, could we end up having a tree split on the same feature or the same field more than one time, just using different thresholds? So it maybe splits on above 2. So 0 to 2 and everything else, it splits there, and then later splits on 5 and above. Is that possible? Absolutely. Absolutely possible, especially if there's kind of an intermediary node. So where we see that it had to split on something else, and then one of those branches, but only one of them, found values above 5 to be particularly interesting. So yeah, that absolutely happens commonly.
Excellent.
All right. Think.
There's one more question though as well that's just come in. We probably just have time for that one, and then we'd probably have to close off. So random seed is an initial random number. So training models with different random seeds is ideal to train. However, does it mean that can we set the same for every machine learning model we train?
So let me see if let me try to. Random seed is an initial random number. So random seed is not an initial random number. It's really just a number we drop into the pseudo random number algorithm. And if we drop the same number in when we first in our process, in a given process, we say, give me a random number. Those numbers kind of are predictable. We get the first one, then the next one, then the next one. They're predictable if you know the seed, if you know what the seed number is. Now, usually we don't know what the seed number is, so it's not predictable to us. However, if we set the seed number, then it's predictable to us, and we know what we're going to get one after the other, after the other, after the other. It'll be consistent if we keep using that same seed. And again, just from a demo standpoint for Glenn and I, it's nice because we know we're going to show you exactly the same thing every time and not have weird variances. But also, it can be nice from a data analysis standpoint just to keep things consistent, not have weird variations when you're trying to keep an eye on what the source of every variance is. Ultimately, it really shouldn't matter much once you're settled and happy and have a model and a training process that you're happy with. It shouldn't matter much. Practically speaking, most people leave a seed in there.
Okay.
From what I've seen.
Cool. Well, I think that's all we've got time for on today's session. as well. So thanks everyone for coming, and we'll see you next week.